The next thing I'd like to cover is what happens when, again, these are just examples of transmission line circuit analysis. So let's say we have a VI and a source impedance source resistance rather, ZS, and let's say we have a transmission line. Of course, we don't know where it goes. So let's see what constraints the source impedance imposes on the incident and reflected waves. Okay, so again, the trick is to realize that at the boundary, the source and the source impedance will impose some conditions based on KCL and KVL, and they must be consistent with the conditions imposed by the transmission line. Namely, the telegrapher's equations must be valid. So the voltage at the, so let's call the voltage at that point V and the current as I. So V is nothing but V plus V minus. I is nothing but V plus by Z naught minus V minus by Z naught. And so V must also be equal to Vi minus I times Zs. That's the constraint imposed by Kirchhoff's law. And putting these things together, we get V plus V minus. That's the voltage V must be equal to Vi minus V plus over Z naught minus V minus over Z naught times Ls. Alright, which basically means that V plus, therefore, times 1 plus Zs by Z naught is nothing but Vi plus V minus into Zs by Z naught minus 1. Which means that V plus is nothing but Vi into Z naught by Z naught plus Zs plus V minus into Zs minus Z naught by Zs plus Z. Okay, so let's do some sanity check. One thing is to say, well, this equation comes out of the math, right? So an obvious thing that we should ask is, why does this make intuitive sense? So sanity check, we set Vi to 0. All right. If Vi is 0, V plus is simply Zs minus Z naught by Zs plus Z naught times V minus. And that makes sense simply because, well, if Vi was 0, we should correlate this with the results we obtained when we terminated the line with a ZL. There we saw that the reflected wave is gamma times the incident wave. And now when you look at this picture when the source was 0, so that this is a short circuit, then the incident wave, the wave that's incident on the source impedance is V minus, and it gets reflected as V plus. So it makes sense that V plus is the reflection coefficient. This is what we'll call gamma S, corresponds to the source reflection coefficient, right? So Zs minus Z naught by Zs plus Z naught times V minus. Now that makes sense. Now let's see. So all that this is telling us is that the forward going wave, when we have an input voltage through Zs exciting a transmission line with a characteristic impedance Z naught, is following. So V plus is caused by two aspects. One is the reflected version of V minus, and V minus is the wave that's incident on that junction between the transmission line and the terminating impedance. So V plus has got two components. One component is nothing but gamma times V minus, and gamma S, just to remind ourselves that that's the source reflection coefficient, and given by Zs minus Z naught by Zs plus Z naught. There's another component, obviously due to the input voltage, and that's given by Z naught by Z naught plus Zs. That makes intuitive sense because if you assume that the line is infinitely long, right, then what happens? There's no reflected wave. So in other words, if V minus was 0, then V plus would simply be the potential divided version of the characteristic impedance Z naught and Zs. So that's basically Vi times Z naught by Z naught plus Zs. Okay, so that's indeed the case as we see from the math. In the special case, when the source is matched to the transmission line, what do we see? V plus is nothing but Vi by 2 plus 0, because the reflection coefficient gamma S is then 0. So what this means is that V minus is incident on the junction, but nothing gets reflected back, and the only wave that's going forward is due to the input and has an amplitude of Vi by 2. Okay. All right. The next thing I'd like to talk about is power along a transmission line, along an ideal transmission line. So let's say you have an ideal transmission line. We don't know where it comes from, where it goes, but at that black line I've drawn, black dotted line I've drawn, the forward going wave is V plus and the backward going wave is V minus. And the power, so the voltage is V plus V minus. The current is V plus by Z naught minus V minus by Z naught. And the power is nothing but the real part of V times I, and that's nothing but the real part of V plus plus V minus times V plus Vi. Actually, sorry, the power is the real part of Vi star. So real part of V plus V minus times V plus star minus V minus star divided by Z. And it's clear that the power is nothing but mod V plus the whole square minus mod V minus the whole square by Z naught plus the real part of V plus minus V plus V minus star and plus V minus into V plus star by Z. And this is a purely imaginary quantity. The quantity in the brackets is a purely imaginary quantity, and therefore this is 0. So therefore the power flowing towards the right is nothing but mod V plus the whole square by Z naught minus mod V minus the whole square by Z. So one way you can interpret this equation is to say that you can think of power going towards the right, and that's given by V plus square by Z naught, and power coming back, getting reflected by whatever is there on the right side, on the load side. And so we know that V minus, if the line is terminated somewhere with some ZL, we know that V minus is nothing but gamma times V plus, and therefore the power is nothing but V plus the whole square by Z naught times 1 minus mod gamma the whole square. Okay, and so this is the reflection coefficient, and this is so this reflects this 1 minus gamma square is basically telling us that of the power that's being pumped into the into the load, a fraction gamma square is getting reflected back, and the net power being dissipated in the load is the incident power times 1 minus gamma square, mod gamma square. All right. So let's again take some examples. So we have an open circuit. Let's say you have an open circuit. Intuitively, of course, it's very clear that no power can be dissipated to the to the right of this this dotted line, and that's obvious, but that also comes out to the math, because we know that gamma is 1, so gamma square is 1, and therefore the power going in being dissipated to the right here is basically 0. The average power is 0, right? Similarly, with a short circuit, gamma is minus 1, and therefore the power being dissipated again is 0, simply because the entire power is getting reflected. Okay. Likewise, let's say this is Z naught. The power being dissipated is mod V plus square over Z naught right? And gamma is basically 0. That makes sense because whatever power is going towards the right, none of it gets reflected. Everything is absorbed in the load, and therefore the entire power that's incident is dissipated towards the right of that dotted line. Now, if you have a purely reactive load, let's call this Jx, where x can be positive or negative depending on whether it's an inductor or a capacitor. What is gamma? Gamma is Jx minus 1, that's ZL minus Z0, by ZL plus Z0. And in general, it's a complex number. However, the magnitude of this complex number is 1, and therefore the power dissipated towards the right of that dotted line is simply 0. Right? Again, because recall that a pure reactance cannot dissipate any power. So whatever power is being is incident must get reflected back. All right. So now the last case. So let's say you have a passive impedance. So you have some R plus Jx. The power being dissipated is V plus. Of course, there will be now some power being dissipated in the resistance. So that to 1 minus mod gamma whole square. This must be less. So less than the incident power, right? So which therefore means that mod gamma must be less than . Okay. So, basically all that is saying is that the power that's being dissipated in the resistor, on the resistor part of the impedance, cannot be greater than the power that's being that's incident in the first place. So, this means that the reflection coefficient must be less than 1. So, in general, for a passive impedance, which cannot, a passive impedance is one which cannot generate energy or power on its own. So, for a passive impedance, the magnitude of the reflection coefficient must be less than or equal to 1. Equal to 1 corresponds to a purely reactive impedance, right? A magnitude less than 1 basically means that the terminating impedance, the impedance has got some resistive part, which is responsible for the dissipation of power. All right. Now, the last aspect I'd like to discuss is the following. This notion of incident and reflected power can also be used to kind of give us a new perspective on power transfer between two impedances. So let's assume, for simplicity, we assume that these are real impedances. So this is Vi, the source resistance, and the load resistance. Now let's assume, let me call this Z0 and ZL. And for argument's sake, I can think of this connection as being an infinitely small or infinitesimal transmission line. with the characteristic impedance of Z. Right? It's a really, really tiny line with the characteristic impedance of Z. Right? So, what is the power dissipated to the to the right of the boundary or that of that dotted line? We know from our discussion earlier in this lecture that the forward going wave is nothing but Vi by 2, right? And the backward going wave is nothing but Vi by 2 times gamma, where gamma is nothing but ZL minus Z0 by ZL plus Z. Okay? And what should be the power dissipated to the right of the boundary? I mean, the power is only dissipated in the terminating impedance. It cannot be dissipated on the transmission line. And why can't it be dissipated on the transmission line? Because we assume that the transmission line is lossless. It consists only of inductors and capacitors, infinitesimally small inductors and capacitors. Okay, so the power dissipated in the load is nothing but the incident power. That's Vi square by 4 Z0 times 1 minus mod gamma square. Okay, and all right, and if we want the maximum power to be dissipated you might also recall that this is what's called the maximum power transfer theorem from your earlier classes. If you want the maximum power to be dissipated in the load resistance ZL, what would we do? We want to make this as large as possible. So that basically means that mod gamma must be as small as possible, and the smallest mod gamma can be 0, right? Which therefore means that the load must be matched to the source. In other words, gamma must be 0. So that's possible only when ZL is equal to Z. Okay. And so if ZL is not equal to Z0, then part of that incident power, the maximum power that can be dissipated in the load is simply Vi square by 4Z0. Right, and this, of course, we knew all this from our earlier classes, where you write the voltage, you write the current, and then you multiply them and you differentiate with respect to ZL and so on. Right, this is another way of looking at the same thing. This, on the other hand, seems a lot simpler to see what is going on. So, if you want maximum power to be dissipated in the load, you want the reflection coefficient gamma to be 0, which means that the load resistance is matched to the source, right? And the maximum power that can be dissipated is nothing but Vi square by 4Z. All right. So with this, I'll stop. We'll continue in the next class.